The following program is brought to you by Caltech.
Good evening. It's my pleasure to be able to introduce Mike Lamb, who is our speaker for this evening. And before I do that, let me just announce the next Watson lecture, which is on April 2nd, and it's given by Sarkis Mazmanian. Say hello to your little friends, how gut bacteria can be harnessed as novel therapies for disease. So that should be a really interesting one. Now let me introduce Mike. Mike received his undergraduate degree from the University of Minnesota in 2001 and a PhD from Berkeley in 2009. And he did a postdoc for a year, and since that time he's been here at Caltech. And for the last 3 weeks he's been a tenured professor. So we're looking forward to having Mike around for a long time, and you'll get to see some of his interesting research. The title of his lecture is When Rocks Roll, How Sediment Transport Shapes Planetary Surfaces. This is a long tradition at Caltech. It started back in the late 40s and 50s when Vito Vanoni and Norm Brooks set up a lab over in the Beckman facility, hydraulic engineering laboratory. And they built, at one point, a 40-meter flume. And this flume, it can tilt, circulate water, and many people in the community of scientists that study the surface of the planets did work in that lab. And today, that work still continues. The flume has been reconfigured by John DeBeery, who now does experiments with a very slow-moving water where he studies propulsion in jellyfish. So this water it's very tranquil compared to what it used to do. And so when we hired Mike, there was a search on to find some space for him to set up the lab. And of course, this facility was once used for the kind of stuff Mike was interested in. But John was doing his experiments there, and so that wasn't really an option. So a search continued, and eventually Caltech found a space for Mike. And we also realized at the same time that he had much greater ambitions. He didn't even want to do moving sand. He wanted to do moving boulders. So the experiments that you see happening here are going on in that facility. And if you've ever gone hiking in the mountains and you get up into the high country and you see a stream bed choked with boulders, and you wonder as you step across these boulders how it is that these things move, when they move, you don't want to be around when that happens. So it turns out nobody's really done much research on this, and that's where Mike has really dug in, and he'll tell you about it tonight. Mike's a guy of amazing breadth and depth. He works on Titan and Mars as well as the Earth. He does experiments, he does theory, he goes to the field. After the station fire a few years ago, he rushed right out with his class and turned that course into an observation of sediment yield when all the vegetation is burned out and it keeps raining. The Hahamunga Reservoir fills up with a lot of sediment in a hurry. Very creative and entrepreneurial guy, and it's my pleasure to introduce Mike.
Good evening. As John said, today I'm going to talk to you about sediment transport and how it shapes not only the Earth, but a few other planets in our solar system. The image that you're looking at up here is actually not in our flume, but is of a river in Idaho, of a camera set down on the bottom of the river. And when I talk about sediment transport, I use this word. What I'm really talking about is this, what you're seeing in this movie, the movement of these cobbles, sand, and gravel being pushed along on the bottom of the river by flowing water. And it turns out that something as simple as flowing water and moving sediment creates many of the dramatic landscapes that we see on the surface of the Earth. Like the Grand Canyon, for example, carved by the Colorado River, water and sediment over time acting against these rocks. You can move downstream to the Amazon floodplain where these beautiful sinuous branches of rivers move across, transporting water and sediment. And even further downstream, this spectacular image from space of the Lena Delta, where the Lena River is pouring into the ocean, and sediment and water conspire to create these intricate patterns. Now, as John mentioned, on Earth, Earth is not alone in our solar system as a planet that is shaped by moving water and sediment. Our neighbor Mars also seems to have this in common. So, for example, these are images from the surface of Mars where we see now long dry, but canyons that look very much like the Grand Canyon, likely carved by water and moving sediment, perhaps billions of years ago. And on the depositional side, we see fan-shaped deposits of sediment that look like deltas on Earth, but again, now long dry. Now that we have rovers that have landed on the surface of Mars, we can get a closer view, and we see this image, for example, from the Mars Curiosity rover of rounded river gravels that are deposited, and a similar picture of river gravels on Earth. The very similar processes apparently happened on Mars of sediment moving and shaping the surface. Now there's another place that's like Earth and Mars and is perhaps surprising to many people, which is the moon of Titan, the moon of Saturn, the largest moon, has what appears to be rivers and sediment transport much like Earth. So this is an image of the surface of Titan, and the areas in blue here are thought to be massive lakes or seas on Titan. And you can see rivers that are pouring into these lakes, likely creating deltas at the mouths of those rivers. But on Titan, it's so cold that it doesn't actually rain water, it rains liquid methane. But liquid methane behaves a lot like water does. Liquid methane on Titan behaves a lot like water does on Earth. It evaporates from the surface, it makes clouds, it rains, it forms rivers, and moves across the surface and collects in these lakes and seas. And just like Mars, on Titan we do also have pictures from the ground. And here again we see cobbles and sand rounded from the transport by water, or methane in this case, on Titan, very similar to what we see on Earth. So the overall goal of the work that we do in my group is try to understand the physics of how water moves sediment and how this coupled flow of water and sediment shapes the surface of Earth and these other planetary bodies with similar processes. And here I show this beautiful picture of this meandering river that has a near constant width and a sinuous planform. And this river got this way not because it has DNA that tells it to form this pattern, and not because people made it this way, but because of feedbacks between these seemingly simple elements, water, sediment, and the topography. And these feedbacks are important. For example, you might imagine if this river was steeper, the water would flow faster, which would move more sediment. And since the river channel itself is made of sediment, this might cause erosion and deposition in the river, which could change the slope of the river or the width of the river. So the river channel itself is an important element in this process. So there's a problem when we want to understand sediment transport over long time scales, over geologic time scales, and that's that geologically significant transport events rarely occur. As John said, when you go and hike in our local mountains, you might step on the same boulders every time you go up there and hike. But those boulders do move, but they might move rarely over our lifetimes. And if they do move, they're dangerous to try to observe. So there's two approaches to solve this problem that we've been using to try to get a better understanding of sediment transport. The first is to study active landscapes. And it turns out that we have one of the most active landscapes in the continental US right in our backyard, the San Gabriel Mountains, and that'll be the focus of a lot of what I'll talk about. But the other approach is to make your own river. So as John mentioned, in our laboratory, we have these chutes that can transport water and sediment, or flumes, like we call them. And these allow us to create our own floods and measure things under controlled conditions so we don't have to rely on Mother Nature. So I mentioned that we live in one of the most active landscapes in the continental US, and that's the San Gabriel Mountains, which is shown here. This is Los Angeles Basin. Here we are here, and if you don't know where we are, we're in Beckman Auditorium, located somewhere in here. Now, this is one of the most active landscapes because the San Andreas Fault runs along the backside of the San Gabriel Mountains. And there is a coupled fault system, a series of thrust faults along the front of the mountain range very close to where we are now. The San Andreas Fault goes through a large bend that's off the image here, and this bend causes rocks to be smushed in between these two faults. This smushing causes the rocks to uplift, and that's why the mountains are there. The uplift rate is rapid. It's about, in geologic terms, about an inch every 25 years, or about a millimeter a year. But these mountains aren't actually rising. The peaks stay at the same elevation. And that's because erosion is equal to the rate of uplift. So whatever rocks are uplifted, this 1 inch in 25 years, is eroded away and shed down off of the mountain range and into the low-lying areas. So the San Gabriel Mountains are active both in uplift and in their erosion rate, which is important for when we want to understand sediment transport because it's the erosion side of the equation that we're interested in. Now, as John mentioned, maybe he didn't mention, but I'm from Minnesota, where I completed my undergraduate degree. And when I moved to Los Angeles and Pasadena about 5 years ago, I had various ideas about what life might be like. And this is one of them, nice beaches and friendly people, happy police officers, and general good community. And really it is a magical place with Los Angeles and the San Gabriel Mountains here snow-capped in the background. But 5 years ago, for those of you who are here, will also remember that this was the time of the largest fire in Los Angeles County history, the station fire, which you can see here is totally obscuring the view of the San Gabriel Mountains. And of course the fire is dangerous, and we have many fires, and we've had many since the station fire. But as you know, it's often, in addition to the fire that we worry about, it's the debris flows and the rapid erosion and sedimentation that happens after the fires during the rainy season. And here's some snapshots from the LA Times after the station fire of some of the areas that weren't as protected from debris basins as others, where cars had moved and houses had been destroyed. Now, of course, this has been a problem this debris flow problem is a problem that plagues many cities that border steep mountain areas. Debris flows are a natural process, and they've been occurring for some time in Los Angeles. And perhaps the most devastating event in the history of Los Angeles was the 1934 debris flows. This is the LA Times from 1934. These storms that also followed fire resulted in about 49 fatalities. You can see here in this map, so here's Foothill Boulevard, if you can't read from that far back, and all of the checkered marks here are city blocks. And what's drawn here are the lobes of debris that have run out across the city, miles over these neighborhoods. And you can see here cars buried. It says, defeated by the elements, these automobiles were hopelessly mired in mud on Glendale Street, 3 blocks north of Foothill Road yesterday. Sweep of waters that dealt death and havoc pictured. So during this event, there weren't debris basins that protect the local communities now from these types of hazards. But it was this particular event that motivated Los Angeles County to construct debris basins. And now most of the steep catchments, steep mountain rivers, end in these debris basins. You can see some houses and cars for scale. This one's largely filled with sediment. And because the erosion rates are so high in the San Gabriel Mountains, these debris basins usually need to be emptied at least every year, if not multiple times a year, for them to continue to protect the areas downstream. So I've done the math on this, and this equals, if you add up all the debris basins along the front of the San Gabriel Mountains, it equals about 20,000 dump trucks per year of sediment. it's a lot of sediment. This 1 inch every 25 years off of the entire mountain range is basically collected in these debris basins and moved away now by dump truck rather than distributed by natural processes such as rivers, so that we, myself included, can live in these nice areas. Now, a curious thing is that after fires, I mentioned that erosion rates really skyrocket. And that's something that, of course, is familiar to most of us that live around here, but why that happens is not really clear. But it certainly happens, and if you do the calculation from the debris basin data, so because LA County, of course, pays for all the dump trucks, they keep track of how much has been removed. And so it turns out that this database is one of the best databases in the world for historical sediment yield from a steep mountain range. Because there's no way that an academic, for example, could afford to collect all the sediment from a mountain range and weigh it every year. But LA County does it for us. But after fire years, we have about 200,000 dump trucks of sediment that tend to be emptied out of these debris basins. So about a factor of 10 times more sediment after fires. So I'll show you this data so you don't have to take my word for it. So this is a compilation of all the data. There's about 100 debris basins, and they've been operating for about 90 years. And if you take all that data and average it, you get a plot like this. Now, this is the normalized sediment yield in millimeters per year. This is essentially the amount of sediment that they collect, and if you were to average it all over the area of the mountain range, you would get units of millimeters per year, or an erosion rate. And this is all plotted in time since there was a fire. So if you look at 10, 20, 30, 40, 50, 60 years since there's been a fire, the erosion rates jog up and down because we have wet years and dry years, but they're mostly constant following this red line. And they're consistent with what we think are the long-term erosion rates, this balance between rock uplift and erosion. But in the year or two after fire, we see that this red line really jumps up. And it jumps up by a factor of 10 or 20. Again, showing that there's a tremendous increase in sediment that comes out of the mountain range after wildfires. So a couple questions that I want to try to address in this active landscape is, where's the extra sediment coming from? And why is it transported after fires by debris flows, these flows that tend to be particularly destructive, rather than normal river processes? And I'll get into the details of what I mean by that. So this is, when I moved here, and before I started working on this problem, this was kind of the state-of-the-art idea, and continues to be the state-of-the-art in many landscapes, although I'll argue to you that it's probably not what's going on in the San Gabriel Mountains, but it's worth understanding what people typically think is going on. So here we're looking at a cross-section of a hillside. There's a river running at the bottom of this hillside, and here's a steep hillside. And normally I think these hillsides have bedrock somewhere down below, a thick mantle of soil. And the way we think debris flows form is that during rainfall, here's the cloud raining, this thick mantle of soil fails as a landslide. And this leaves a scar that you see here. And this material, the sediment and the water mixes, becomes a debris flow, runs down the hillside into the river channel, and then runs down the river channel into your house or the debris basin. So the key thing here is that the debris flows initiate on the hillside within this thick mantle of soil. Now, the connection to wildfire is that plants like these trees drawn here, their root network provides some strength to the soil. It stabilizes it. So if you burn the trees, you reduce the strength of the soil. Then when you rain on it, it's more likely to fail and create these debris flows. And this is often what we hear about in the news locally when we have this worry of debris flows. So this is a clip from the Associated Press from just this month, March 1st, when we had the big rains a couple weeks ago, and saturated slopes worry California cities. And often what we hear about is that the hillsides are coming down. And this idea that the hillsides are coming down is based on this cartoon that there's a thick mantle of soil, a big reservoir of soil that's about to flush down these hillsides after rain. But there's a problem with this hypothesis, especially for the San Gabriel Mountains. So what I show here is a high-resolution topographic map with the image of the San Gabriel Mountains overlain on the top. This is Mount Lukens. And what I want to point out is that everything that's colored red here have slopes that are greater than 45 degrees. And that's very steep. If you've ever tried to get sand to stand at an angle of 45 degrees, you were probably unsuccessful. And that's because sand's stability angle is about 30 degrees. And any slope that's greater than that, the sand will simply roll downhill by gravity alone. No rain needed. So these red areas, which comprise a lot of the terrain of the San Gabriel Mountains, don't have stable sediment mantles. They don't have these thick soil mantles for landslides and debris flows to occur in because they're so steep. And this is true especially after fire. So plants do provide some stabilization on these slopes, and I'll show you some examples. But after fire, these hillsides are nearly completely cleaned of sediment before there's been any rain. So here's some examples. So this is after the station fire and before any rainfall. So all that's happened to this landscape is that the plants have burned. And what I see here is that up above this dashed line, you're looking at a steep hill slope that's basically barren rock. There's no sediment on this hillside. There's not a thick mantle in order to create a landslide and create a debris flow. Instead, all the material that was up here is now sitting at the base of the hillside in this lower sloping river channel, these loose sediment cones that you see here. Now, if you went hiking after the station fire, you might have seen something like this. So this loose material will stop at any angle that's less than its stability angle of about 30 degrees. And that includes fire roads like this. So again, barren hillsides without any sediment on them, and all the sediment is stuck on these lower sloping terrain. And the firefighters will tell you that this is a major issue. This sediment comes down during the fire. This is happening hours into the fire, and this, of course, makes the fire roads very difficult to drive across. But most of the low-sloping terrain in these landscapes are the river channels themselves. So here's another example. Here we're looking at a river channel now buried in this loose sediment that used to be trapped up on the hillsides, again, before any rain has happened. So there is no sediment on the hillsides to create debris flows. It's all sitting down here in the river channels. This is in Glendora, in the area that burned and was of concern just a couple weeks ago. So this leading idea that there's a thick soil mantle may apply to a lot of landscapes, but it doesn't seem necessarily appropriate for the San Gabriel Mountains. Instead, there's a new hypothesis that we've been working on, which I'll give to you here in cartoon format, and then work through some of the details we've been doing to substantiate it. So it goes something like this, that instead of a thick mantle of soil on the hill slopes are relatively barren. They're mostly bedrock, except for local stability of sediment that gets stuck behind plants. And if the plants weren't there, this sediment would simply roll down off the hill slopes by gravity alone because the angles are steeper than the stability angle for that sediment. So then when we burn these plants during a wildfire, all this material that was locally stuck on the hill slopes collects in the bottom of the channels even before there's been any rain. So this is a dry process. Then that material sits and waits for rain. The gun is loaded, so to speak, and all we need is rain then to trigger these debris flows. But this means that the debris flows that we see are coming from the river channels themselves, not on the hillsides. And that's something that people haven't considered before, nor have they thought about how actually that might work. So the problem of debris flows and fires and these connections and our local hazard problems that I've talked about so far sit in a broader context of questions that we don't really understand about how steep bedrock landscapes like the San Gabriel Mountains work. And so although I'm going to talk in detail about the San Gabriel Mountains, I'm really attempting to use it as a case study to understand the basic physics of how these processes work, not only here but in other landscapes. And there's three questions that I'm going to structure the rest of the presentation here about. The first is what controls sediment storage and release on steep bedrock slopes. The second is, once we get this sediment into the river channel, when does it move? And as John mentioned, when you hop across these boulders, are they always there or when do they move? And we know that there's two modes by which sediment tends to move out of steep river channels. One is by river transport, and the other is by debris flow. So we want to know, when does sediment move by rivers, and what is the trigger for debris flow initiation? So we're going to step through these three questions now. So for the first one, as I've already alluded to, the hypothesis is that sediment is trapped by vegetation on these steep slopes, and it can be abruptly evacuated after wildfire prior to any rainfall. And here's an image to substantiate some of the cartoons of a yucca here with a wedge of sediment that's basically stuck upslope. The vegetation acts as a little dam. And as I've already motivated, after you burn the vegetation, then you see evidence for all this sediment that accumulates at the bottom of these hillsides. So I'm going to dig into this idea a bit more with formulating a simple model, adding some field measurements and lab measurements, and then applying it to our local mountains. So the model is basically a balance of mass. It works like this. This is a hillside, steep hillside. Here's my cartoon plant with my wedge of sediment stuck behind it. And the idea is that sediment is continually produced from the bedrock everywhere on the hillside at a rate of about 0.5 millimeter per year. This is the rate that balances the long-term uplift of rock. But because of the steep hillside gradients, most of the sediment simply rolls off the hills and into the river channels and flushed out of the system. But some of the sediment is trapped by plants in these local dams. And of course, then if you burn the plants, the sediment will be inherently unstable, even without rainfall, and will flush into the channels. So let's see if any of this makes sense. So first, I want to point out the importance of these steep slopes. So I've mentioned it a couple of times, but just to make sure we're all on the same page, here's a movie from some simple experiments we've done in the laboratory where we tilt a board steeper than the angle of stability for this sand, so steeper than about 30 degrees. And you can see if you pour sand in from the upstream end, it all just rolls off the board. Okay? These are fun. This is cutting-edge stuff at Caltech. But now if you put vegetation at the bottom of the hillside, some of this sand doesn't roll off the board anymore, but it collects in this wedge of material. Now, a lot of it bypasses the wedge and goes around the boundaries, but depending on the size of the plant, you get different amounts of sediment that accumulate here. And it's release of this accumulated sediment on the hillsides that I'm arguing is the extra sediment that we see after fires. Okay, so what can we do? Well, we can go out and measure how much sediment is actually stuck behind plants. So this work has been led by Roman DiBiase, who's a postdoc here in my group, and he's going out and digging up the soil that's trapped behind plants on steep hillsides. And the picture is at a funny angle here, but this is quite a steep hillside, and Roman's probably about to fall over. So this isn't easy work. And we've done this for a number of different plant species and different types, and trees. Here you can see trees with a sort of wedge of material stuck behind it. And this is the kind of data that you get if you go do that for a summer. Is you get the measured volume of material in cubic meters here that's stuck behind a plant, and it scales largely with the width of the plant. So you might expect bigger plants trap bigger piles of material, and that's what we see. And in fact, it follows a cubic relationship, so the volume goes like the width cubed. And what this means is this is what you would expect if these are basically pyramidal wedges of sediment that are trapped behind the plants. So it seems to be making sense with the cartoons that I've drawn so far. And you can see a number of different species of plants here, and they all seem to follow more or less the same relationship. So we can also go and do these types of experiments in the laboratory, and I already showed you the movies of these experiments with our tilt table and our plants of different width. And these are nice because we can isolate different variables that are hard to separate in the field, like the effect of different sediment sizes, the effect of different slopes, the effect of different plant sizes, etc. One of the more important things that came out of these laboratory experiments is the effect of the angle of the hillside. So what I show here is a summary of the results from these experiments, where what I'm plotting is the soil thickness, so the amount of soil that's trapped on the board, essentially on the hillside, as a function of the angle of the hillside. So 15 degrees is a fairly low-sloping hill, 50 degrees is very steep, 30 degrees is that threshold angle for stability that I've been talking about. So what we see is that below 30 degrees, sediment is stable, unconditionally stable on the board. It won't roll off. And that puts us into these landscapes that are sort of the typical model that people have been thinking about with the thick soil mantle. And if we go very steep, say 50 degrees, then there's no sediment that basically sticks on the hillside, even with plants. And so this would be a rocky landscape way over here. But there's this wedge of parameter space here drawn in yellow for slopes between about 30 and 40 degrees, where there can be a substantial thickness of soil that's trapped by these plants on the hillsides. And if the plants weren't there, that sediment would be unstable and roll off. So this is unstable soil that's being locally trapped. So what we can do now that we've done these measurements in the field in the laboratory is we can go out to a real landscape and try to figure out how much sediment might be trapped on hillsides that are between these angles of 30 and about 45 degrees, where sediment is stable from plants, but only stable if the plants are there. And it turns out that that's most of the landscape that you see. So this is, again, the high-resolution topography from the San Gabriel Mountains. And what we've done here is classify with the different colors the regimes from that previous plot. So what you're looking at here is the gray ring around the top here is the ridge line. If you're standing up on the very top of the hill slope, you'd be standing on the gray. And the river channel is this other gray streak that goes down the center. The gray areas are areas that are less than 30 degrees. That's areas where sediment would be stable. And that's areas where this traditional model of landslide-driven debris flow should apply. And you can see that that comprises a very small part of the landscape. Instead, most of the landscape are in these orange colors, which are between these slopes of 30 and 45 degrees, where we would expect sediment to only be stable if plants are there. And then if the plants burned, that sediment would be unstable and it would rush down slope and collect in the nearest place that was less steep, and that would be this river channel at 30 degrees. So since we've quantified how much sediment can be trapped on these different slopes, we can predict how much is actually there. And remember, we have something to compare it to because we have this debris basin record that says that there should be about 10 times the sediment yield that comes out of the landscape after fire. So at least to check to see if this is a reasonable idea, we can see if those compare or not. So to do that, we plug these measurements all back into this conceptual model that I brought up in the beginning. And let me step you through just an example simulation that we can do with this model. So the first thing we need to do is be able to model how plants grow. We're doing this in a very generic way. Of course, the world's more complex than this, but we have to start somewhere. So here's our plant, and it's growing, and it grows in size over time. And so it grows and it reaches some stable size, and then there's a fire and it burns, so it goes back to size 0. And then it grows again, and then it burns and it grows again. And this return period of about 30 years is typical for the San Gabriel Mountains, meaning that fire burns the same place on the ground about every 30 years if you do the statistics in the historical time here. Okay, so of course, just the plants growing up doesn't mean that there'll be sediment there. It also takes time for these reservoirs to fill up with sediment because sediment's being produced from the bedrock, and that's happening at a rate of about 0.5 millimeter per year. So just as we talked about in the cartoon, it takes time for these wedges of sediment to grow, even if there are plants there. And that's what's shown here is the amount of sediment that's being trapped by the plants, again, as a function of time. So as the plants grow, the amount of sediment stored also grows. Eventually, though, the dam reaches its capacity to hold sediment and levels off and has filled storage, as I show here. And then, of course, if you burn the plant, the amount of sediment storage on the hillside drops to 0, then it ramps back up and drops to 0. So what does this mean if we look at the base of the hill slope? So if we put in parameters for the San Gabriel Mountains and we look, how much sediment is going to come out at the bottom of a hillside in sediment yield, millimeters per year, we see that the rate is around the background rate, about 0.5 millimeter per year for most of the time, sometimes a little bit lower because sediment is being caught by the vegetation and not making its way out to the bottom. But then when we have a fire, of course, we get a big pulse of sediment yield that's associated with release of this dam. And the magnitude is important, so the background rate's about 0.5 millimeter per year, and the pulse that we predict out of this model is about 12 millimeters per year. And what I bracket here in the bar is the observed sediment yield that we get in the fire years from the debris basin data. So it seems that this sort of simple idea of little dams being formed by vegetation, they could account for the tenfold increase in sediment that we see after fires. Okay, so to summarize this section, which I raised the question, what controls sediment storage and release on these steep bedrock hill slopes? This is what we think is going on, is that sediment is transiently stable due to vegetation on hill slopes that exceed the angle of repose, this angle of stability. That after wildfire, the sediment is stripped from the steep hill slopes, and the amount that we calculate could be available matches with the tenfold increase in yield that we see in the debris basin data. So coming back to the debris flow question, again, what this means is that these debris flows must initiate in sediment that's already accumulated in the river channels prior to any rainfall, rather than the hillsides giving way like we typically hear about. So this leads us to the next part of the presentation, which is to investigate, once we get sediment in a river channel, in a steep river channel, when does it move? And when does it move by normal river processes, and when does it move by debris flows? So we'll start out with the river. So if I haven't convinced you yet that the sediment accumulates in the channels, here's a picture from the San Gabriel Mountains before the station fire in 2006 with a fiery graduate student jumping with, hopefully this pool is quite deep. And here's after the fire in 2010 with the graduate student who's less happy because he doesn't get to jump in the pool, and he has to hold this survey rod while we measure how much sediment accumulated in the channel. But again, here we're asking, when does this sediment move? And the hypothesis is relatively simple. It's been around for a long time, 100 years or more, and it's simply that larger particles require proportionally larger water force or hydraulic force to move. And this should be reasonably intuitive, that if you have a bigger boulder, that it should require proportionally more force of water to get going. So just to illustrate that, here's some experiments that we've been doing in the Earth Surface Dynamics Laboratory, measuring directly the forces on particles. Here the particle is a bowling ball. It happens to be an easy sphere to buy and relatively cheap. So this bowling ball is sitting on the bottom of this riverbed in our flume, and I'm not going to talk in detail about this, but just to illustrate the point here that, of course, the water is pushing against this bowling ball, and that's creating this force on the bowling ball that I'm going to call the water force. And what's resisting the bowling ball from moving, of course, is its weight. And so you might expect if the particle weighs more, you require proportionally more water force in order to move the particle. And so we're going to talk for quite a bit of the rest of the time about the ratio of water force to particle weight. So if you always require proportionally more water force to particle weight, that means the ratio of these two things should be a constant value. So we're going to look at this plot for a long time, so we better make sure that we all understand it. And the y-axis here is the water force relative to the particle weight. So as we move up on this axis, this means we're having larger forces of water relative to the weight of the particle. And as we move down, we're having smaller forces of water relative to the weight of the particle. So, and I said that this, you should intuit, or I gave you the hypothesis, that this should be a constant value. And the constant that's often used for most rivers is this value of 0.045. And that's just empirically determined. People go out and measure when things move, and that's the value that they find. So this value then separates these fields of no motion. Below this line, there's not enough water force to move the particle, so there's no motion. And above this line, there should be plenty of sediment transport. And the criteria where just when sediment starts to move is at the line. And that's the concept that we're going to try to investigate, is just when sediment starts to move. And what I've plotted it against here is the slope of the riverbed in degrees. So zero slope is a low-sloping river like the Mississippi. It's not exactly zero, but it's 10 to the minus 5, so it's quite low. But when we get into steep mountain terrain, we can have river slopes of 10, 20, even 30 degrees. Okay, so rivers across this wide range in slopes look different. And just so we know what we're all talking about here, here's a Russian river, which is a fairly low-gradient river in Northern California. It looks nice, and I go swimming here sometimes in the summer. And here's Big Pine Creek in Owens Valley, which is steep. And you can notice right away some differences, right? So the steep river has these big boulders stick out of the flow. The flow is very rough and rolling over the boulders. And so you might expect that things might be different. Sediment might move under different criteria in the low gradient rivers compared to the steep rivers. But this actually is something that hasn't been investigated too much before. So when I started this project, I wanted to compile all of the data that existed from experiments like flumes and from measurements that people have done in the field of when sediment first moves and put them on this plot and see what we know. And this is what we know. So this is about 100 years of everybody's data collected and put on this plot. And again, these are points of just when sediment starts to move. So anything below the points would be no motion, and above the points would be lots of transport. Okay, a couple things to note. First is that there's almost 0 data points in the channel slopes, these steep slopes that dominate steep mountain terrain like the San Gabriel Mountains. So if we were going to come up with a model to predict when the sediment would move, we would have to rely on the data points that we have for the Mississippi River. And it's not clear if that's appropriate or not. The second thing is that, if anything, these data don't seem to be following the constant, but they look like they're increasing with increasing channel slope. And that's actually fairly counterintuitive and really confused me and still confuses people to this day, but I think it's right. So this means, of course, that in steeper rivers, it requires more water force for the same particle size for the sediment to move. And you might expect the opposite to be true, that on steeper rivers, sediment should move easier because it's steep and gravity should be helping things along. But the data actually suggests the opposite, that sediment is more stable on steep rivers despite the fact that gravity must still be helping things along. Okay, so we wanted to dig into this to see if we can explain this trend, also to populate this area of this phase space that doesn't have any data points. And by the end of the presentation, I'm going to fill in all this white space. So we'll have lots of answers that we can think about. So we're going to do this with a little bit of theory, field measurements, and lab measurements again. Okay, so the important concept here, though, about what's really changing in a steep river compared to a low-sloping river is the flow depth relative to the particle size. And this is something that I alluded to with the pictures of the Russian River and Big Pine Creek. Now here we can see it in our experiments with the bowling ball. If we tilt the flume to be very steep, we see this very energetic water flow. But most of the water in this example is moving under the particle rather than over the top. But you see in the deep flow, it looks much more tranquil. But there's actually much faster water moving over the top than the bottom. And this has a big impact on the criteria for when sediment moves. And it turns out that, or at least we hypothesize, that shallow and rough flows, such as this steep case, produce smaller hydraulic forces or smaller water forces due to the relatively slow flow at the particle top. Again, this hypothesis may seem counterintuitive since this flow looks so energetic. But what we really want to know is not the energy in the water, but the forces on the particles. And if this hypothesis is right, it could explain why we see this trend in the data that sediment is apparently more stable in steeper river channels. I should have said earlier that if you do go hiking and boulder hopping, it should be relatively intuitive, perhaps to you, that sediment is more stable in steep mountain channels. If you go to the Mississippi River, for example, sand is moving constantly in the Mississippi River, whether it's in flood or whether it's in low flow. If you were to snorkel down to the bottom, you'd see sand moving by. But if you go to our local creeks, there's boulders that have probably been there for many decades and haven't moved. So I think a hiker's intuition is that sediment is relatively stable in steep channels, but the physics aren't exactly clear. So we put together some ideas that have to do with this shallow, rough flows versus deep, low-sloping rivers, and plug those into a force balance model to come up with a new theory of when we think sediment should first move. And that's shown here in the red line. And this theory it better tracks the data that exists that suggests that sediment actually is more stable in steep slopes. Okay, but we still have this problem that there's no data points. And so the rest of the talk, I'm going to try to fill in this data. And particularly, again, I'll point out that these steep slopes comprise most of the river network that we see in steep mountain terrain. Okay, so how do you measure when sediment first moves? Well, it turns out that it's pretty difficult to do. So there's a reason why there aren't a lot of data points in that region. And it's the reasons that I listed earlier in the talk, that sediment rarely moves. And if it does, it's often dangerous to measure. And we don't have any sophisticated tools. JPL so far hasn't developed a satellite that can measure when sediment moves. So we rely on the tried and true method of spray painting sediment, waiting for it to rain, coming back and seeing what sediment moves, measuring the sizes of that sediment with a ruler. Of course, we need to know not just the sizes of sediment moves, but we also need to know the water force that moved that sediment. So we do that by instrumenting these rivers, like this one here in Northern California with a series of pressure transducers. These allow us to reconstruct the floods that came through these rivers and calculate the hydraulic forces on the particles. And we did this, as I mentioned, in Northern California in the Eel River watershed. We surveyed 5 creeks with slopes up to 20 degrees, so much steeper than had been measured previously, and monitored these creeks over a series of about 5 years. This work was led by graduate student Joel Scheingross, who's a PhD student here. Okay, so here's the data. We observed 7 floods over these 3 years. Joel recovered 1,510 grains. This was a lot of work, and we got these 5 data points. So you can see them here, these red points here. And the data are a little bit scattered because the field has a lot of complications. But they nonetheless show that this water force relative to particle weight can be quite large, especially as we go to steeper and steeper slopes. Now these values, this is a logarithmic scale here, so these values up here are some 50 times larger, 50 times more water force required to move these particles than we would have expected if we would have applied the logic and theory that we know from low-sloping rivers. Okay. So as Joel will tell you, this was a lot of work in part because it's boring to sit around and wait for it to rain. So the other solution to this problem is to make our own rivers. And this is the PhD thesis of Jeff Prancevic, who's still here, who's been doing experiments in this flume in our laboratory where we can fill this channel with gravel, you see the movie here, tilt it to different slopes, run water of different discharges over it, and observe when sediment first moves. And you see here in this picture, this is a condition that's pretty close to initial sediment motion. So here's gravel, and you can see this gravel rolling slowly over the top. So it's not moving very fast. It's close to this initial motion of sediment that we're after. And again, because we can tilt this to any slope we want, we can go after these steep slopes that haven't been investigated before. And what you see with the laboratory data are these red circles, which track the theory quite well and show and confirm, indeed, this trend of increasing water force required to move sediment relative to the particle weight as we increase the angle of the bed. So again, it seems that this idea, the key here is that the water in these steep channels is shallow relative to the particle size. And so even though the channels are steep, and gravity should be helping the grains move along, this change in the hydraulics to this very rough condition tends to reduce the water forces on the particles. Okay, so this again separates now these fields, this line or these data points separate where we have no motion, grains don't move, and as we increase the water force, if we picked a bed slope, increase the water force more and more, eventually we cross this line, sediment moves, and as we go higher and higher, it moves more and more. So this is the end of the part about rivers, and the summary here is that grain stability is enhanced in steep mountain channels compared to lowland rivers by up to 5-fold due to the reduced hydraulic forces in shallow, rough flows. And the results indicate a decreased role of river transport at steep slopes. And this is the key tie-in back to the debris flows that we're supposed to be talking about. And that's because if sediment isn't moving by rivers in these steep channels, it has to be moving by some other process, and that's debris flows. So what is the trigger for debris flows? So we're all on the same page. A debris flow is not a normal river. And here's some movies from debris flows showing these highly concentrated snouts of the debris flow carrying large boulders long distances. And it's the power of debris flows to carry such large sediment that make them particularly dangerous. We often hear after fires about on the news about mud flows. These aren't mud flows, these are boulders, and debris flows can carry sometimes house-size boulders, often car-size boulders. And a car-size boulder is a lot heavier than a car. You know, a car is mostly filled with air. So if you want a first-hand account of what it's like to experience a debris flow, you can talk to our very own Professor Andy Ingersoll, who's a planetary scientist here at Caltech. And in 1969 was another bad year for fires and debris flows. Andy lived behind the line of protection, behind the debris basins in Santa Anita Canyon. And during this time, his cabin was run over by debris flows. So at the time in 1969, Andy was an assistant professor, 10 years before I was born. Sorry, Andy. And Andy was interviewed in this book, which is a great story about this fight that Los Angeles has against the debris flows. If you haven't read it, it's by John McPhee. The third chapter is called Los Angeles Against the Mountains. And Andy was interviewed by John in this, for this book. And when he asked him, you know, you're a geologist, you talk to people that study these things, why are you living where your cabin can get hit by debris flows? And first he said, in those days, everybody was some kind of hippie. And then he concluded that it was just a lot of fun anyway. Okay, so remember debris flows. Our hypotheses here, the one we started with, the sort of ideas that were out there prior to the work we've been doing, is this idea that there's a thick soil mantle on top of the hillsides and that the debris flows are coming from landslides, coming from failure of this thick soil. But now we're starting to think about the problem differently. We're thinking that all this sediment has accumulated in the bottom of the channel, and when it rains, the debris flows initiate in the channel. So I showed you this picture before of loose sediment accumulating at the base in this river channel, dry. This is, again, from the Colby Fire area in Glendora, just from this month and last month. And we went up there right before we had the big rain a couple weeks ago. And this is what we saw, is hillsides that largely have stripped sediment and these cones of loose material that have filled in the bottoms of the river channel. So it looked like it's not the hillsides that are going to give way again, it's this channel fill at the bottom. So we put up, in our haste, a time-lapse camera, and so what you're seeing here is the same picture here, just a little bit lower resolution because of the camera. But here are the cones, and so I'm going to run through this. It's going to go fast, but you'll see several pulses of rain that happened during the storm event over a period of a couple days. And if you keep your eye on the sediment cones here or over here, you'll see that that's the material that gets swept away in these debris flows. So there goes one, and then another pulse, and another one, and another one. And these are certainly debris flows because these images, these pictures occurred every 10 minutes. So when you see them, they're in one picture, then they're gone. And so there are these pulses that go through the system and clean everything out. And if you go up to the same area, this is the same thing after now, you see that what's missing, you can look up at the hillsides, they're mostly the same. There's little plants up here that are still there. It's all the material that was filling in the channels that's been evacuated. Okay, so why is sediment transport by debris flows rather than by normal river processes after fire? So to answer this, we can go back to the experiments, try to make things happen on our own. So this is the movie I showed you before of sediment rolling over the top of the gravel riverbed by normal river transport. But if we steepen the flume up to about 30 degrees and run water through it, what we see is something quite different. That you can see here, instead of a couple grains rolling over the top, the first sediment motion that we see is a complete failure of the riverbed, which would cause a debris flow. So just like the river transport case, we can map out the conditions in which we see debris flows occur. And this is our favorite plot that we had before of the water force relative to the particle weight, plotted versus the bed angle. And here, these points are points where we observe this failure of the riverbed. So for below these conditions, the bed is stable, and above these points, the bed would fail. And you can see as we go to steeper slopes, it requires less water force to cause these failures, which you might expect because gravity should be helping things along on the steeper slopes. Now we can plot our river transport data on the same plot, and I told you I was going to fill in all the white space, so here is the filled in white space, which now gives us a complete picture of when we would expect sediment to move by river processes and when we think it should move by debris flows. So just to walk through here, if we picked, so we have these different fields. We have the green, no motion, where sediment should be stable. The white here is where sediment should move by river transport. And the purple is when we should have debris flows. Interestingly, it turns out that steep channel slopes about 26 degrees is where sediment is the most stable. If you were up here and you had this water force located here and you moved to a lower slope, you would have river transport. And if you moved to a steeper slope, you would have mass failure. And it shows here that at any slope less than about 26 degrees, the first motion should be by river transport. And for slopes steeper than 25 degrees, the first motion should be by debris flows. Okay, so what does this have to do with fire? Well, now that we have this map of where we expect sediment to move by different ways, we can explore some scenarios of what fire does to the landscape and why debris flows might be more likely then. So why should a channel filled with this loose sediment after a fire be more likely to cause a debris flow? So here's our favorite diagram again. And what we can do is plot what normally happens on this diagram. So what normally happens is something like this blue line, that when we have a flood, when it rains, the water tends to move sediment just above the threshold of motion. So that sediment moves, but it doesn't move very vigorously. And so if we're at a 5-degree channel slope, for example, we tend to have this water force, which would be in the river transport regime. And we have to go up to slopes of about 23 degrees to get into the debris flow regime. And this is consistent with what we observe in mountain regions, is that most of the river network moves sediment by normal river transport. And it's not until the very steep slopes that we see debris flows, at least outside of fire times. Now, there's two ways to get debris flows to happen in more of the river network, and all of them involve getting up into this parameter space up here. So they all involve high water forces relative to the particle weight. So there's two ways to do that, and one is to have a very high water force. So if you had an extreme flood event, that would shift this curve up and you'd have more debris flows at lower sloping channels. Now, after fires, that doesn't always happen. But what fires do is they deliver a lot of fine sediment into the river channels. And remember that it's the water force relative to the particle weight that matters. So for even the same flood event, if the particle size is much smaller, we're going to shift up into this higher regime. And that's what we think is going on after fires, that this pulse of fine sediment, here shown a factor of 10, but it could be much as 100 times finer, this moves our typical flood on this yellow line, which means that only channels with slopes less than about 5 degrees are in the river transport regime now, where the bulk of the river network is in this mass failure or debris flow regime. Okay, so to summarize these ideas about wildfire and debris flows, we think what's going on is that first, wildfire destroys the vegetation dams, and these channels are loaded with relatively fine sediment, and this happens prior to any rainfall just by gravity delivering sediment down into the channels. Debris flows initiate in the channels due to this abrupt loading of fine sediment, which shifts the transition from river to debris flow transport to these lower sloping river channels. So there's a significant implication to this, at least one, that I want to point out here, which comes back to the differencing between the standard model and the new model. And the standard model says because there's this very thick mantle of soil, that if you had a greater fire frequency, which is something that's predicted because of climate change going into the future, that greater fire frequency should result in more debris flows because we have this infinitely thick mantle of soil which to draw upon and create landslides and debris flows. But our model says something different. It actually says if there's greater fire frequency, then these sediment piles should be smaller. There's not as much time for the piles to get as big as they normally would be, which is going to reduce the loading into the channels and potentially cause smaller or fewer debris flows. So whether you're in this soil-mantled landscape or bedrock landscape could make a big difference about how you potentially are going to manage changes in fire frequency. Okay, so I want to step back now away from the fire debris flow problem and just have a couple slides of closure. First is, in addition to investigating our local hazards, along the way we've learned some fundamental things about how steep bedrock landscapes work. And I raise these three questions, and I'll sum up with three answers about what we think is going on here. And the first, as I just mentioned, is that sediment on steep rocky hill slopes is transiently stable due to vegetation, with the potential for these abrupt pulses after fire. And that sediment is more stable than expected in steep rivers because of the reduced hydraulic forces associated with shallow and rough flow, and that debris flows can develop from failure of the channel bed rather than on hill slopes, and these failures are more likely during large floods or after large inputs of fine sediment. Now, I want to step back even further because I think that these lessons that we've learned in California and in our backyard in the San Gabriel Mountains, they should apply broadly if we have the physics right, and perhaps even to other planets. So I introduced talking about some of the processes on Mars and Titan, and I don't have time to go into the detail, but I just want to come back to them briefly. So for example, if we look at Mars, and I showed this image earlier, that we see Mars today has these dried river canyons that look perhaps like the Grand Canyon, but suggest that there was water flowing in these canyons some time ago that carved them. And we want to know how much water, for example. Now here's an artist's rendition of Ron Miller's of one of these canyons with waterfalls pulling over the top, carving these canyons. And we know that water flowed in these areas, and it was probably a long time ago, very long time ago, perhaps more than 2 billion years ago. But how much water? Does Ron Miller have it right here? Should there be 10 times this much water, or should there just be a trickle in these canyons? And the work that we're doing and learning in the San Gabriel Mountains helps a lot with these problems. And probably one of the most useful things that we've figured out is the diagram that describes the water force relative to the particle weight. Because we know to carve these canyons, you need to move the sediment through them. And on Titan, as well as Mars or Earth, we have observations of sediment. Sediment that moved, which means we can measure the sizes of sediment, which means we know something about the particle weight. So we can run this problem in inverse and infer the water forces that are required to move this material, or the water that may have flowed over these planets or even over our own Earth long before we were here. So if we know something about the water force, we can infer something, for example, about the amount of water that flowed in these river channels and potentially even how much it rains. And so sediment transport physics are being used at the cutting edge now for problems, for example, on Titan. And the first calculations of how much it rains on Titan were made from calculations based on observing the sediment size that moves across the surface. And it turns out that Titan rainfall rates are probably pretty similar to what we see on Earth. So understanding the physics of sediment transport is crucial for unraveling the climatic history of Earth and other planets. Thank you.